Is my screen visible? Am I audible? And is my screen visible? Okay. So, just for an introduction purpose, so welcome to the live session of problem solving session for the course Geotechnical Engineering 1. This is the third week we are meeting. So, I am Yogendra Narayanan. I am a PMRF research scholar, and this course is being handled by Professor D.N. Singh from IIT Bombay. So the primary purpose of this course is to revise the concepts and solve some problems uh, corresponding to the contents of the particular week to make the learners proficient with the concepts uh, and give an extra uh, support for uh, for approaching the problem, which will be useful for their um, in NPTEL exams as well as further examinations and uh, professional career ahead. So, with this, a brief overview of what has been covered in week 3 contents is especially the concentration has been laid in clay mineralogy and some of the parameters that are associated with it, and what are all the different types of clay minerals, their arrangement, their structure, what is their behavior, how to what governs the behavior, and etc. So with this, so this will be more of a theoretical session since there are no since this week does not contain much of numerical aspects of the subject. So most of the discussions will be theoretical and subjective. So I encourage all the learners to ask questions and engage in uh, active discussion in order to uh, in in order to uh, move this session in an interesting manner. So with this, we will come some of the questions which we have is, so specific surface area SSA is defined as, the first question, specific surface area is defined as option A, total surface area by mass, option B, total surface area by volume, option C, total surface area by thickness, and option D, total surface area by length.
Yes, sir.
You can say the answer.
Total surface area by mass.
You are not audible. Please check your audio once.
I'm audible, sir.
Yeah, now you are audible.
First one, sir. Total surface area by mass.
Okay. So, how do you calculate it?
Uh, I'm not aware about it, sir.
Okay, I will give a small idea on how it is calculated. Right. So, the total surface area is first let us consider. um, so, let us consider this grain. There are some grains which are touching each other. This is a very simplistic simplistic representation, and connect all the centers, and let the diameter of all particle be d. So this length will be how much?
4D.
No, this single side of the square will be d, right?
Yes, sir.
And the surface area will be d square.
D square.
And how many faces are there?
4, sir.
Now it is consider it in a 3D.
6.
6 faces. So the total area will be 6d square, right?
Square. Yes,
Now
sir.
you have to calculate the mass, right? Mass, how can you calculate is you mass is defined as density into volume,
Volume.
right? So volume you know which is d cube,
Yes, sir.
right? Density, how will you calculate? Specific gravity of the sun is into density of water,
Standard water.
right? Understood? So this is how specific surface area is calculated. And if you see uh, when you decrease, now you can cancel this d square and d, right? So specific surface area is inversely proportional to 1 by d,
Yes, sir. 1 by D.
1 by d. So now you will understand. So now you see, now as you rightly mentioned, the total surface area is specific surface area is total surface area per unit mass. And in some other fields like earth sciences, it is also defined as per volume also. So but in our subject we define it as total surface area by mass only. All right, so
Okay,
don't
sir.
get confused in it. So now coming to the question 2, increase
Wait,
in,
sir. I will note.
yeah.
Proceed, sir.
So now coming to question 2, so increase in specific surface area leads to reduction in particle size and reduction in activity, increase in particle size and increase in activity, increase in particle size and reduction in activity, and reduction in particle size and increase in activity. So increase in
Sir, reduction in particle size, sir.
ah
Uh, Particle size may be reduced,
yes,
but I'm not aware about activities.
okay. So how you are saying particle size is reduced?
Sir, I could let gravel see, sir. The
Mhm.
specific area is less, but mass will be very wide, na, sir.
Yes.
That's why specific surface area will be less.
Okay. Another
Compare it.
simple, this is what we have already seen from this relation, right? SSA is
Yes, sir.
inversely proportional to
Proportional to diameter.
particle diameter, which is a representation of particle size. And the person who has joined recently, you can start following and start discussing with the second question onwards. So now as specific surface area increases, particle size will start decrease. So it is actually the either way. Uh, it is in a other direction. So if the if the particle size starts decreasing, so specific surface area starts increasing. So and activity is the property of those of the particle to interact with the external agents. All right. So once the specific surface area is becoming larger, so there will be more space available for the surface interactions to occur. Understood?
Yes, sir.
So then that's why larger the specific area, the activity will be higher. So how the specific surface area is becoming higher? It is due to the decrease in particle size. So this is how it is connected. All right. Any doubts?
No, sir.
If you have any doubts, you can interrupt me at any time and get get yourselves clarified. And now
Okay, sir.
I am saying it as a qualitative term for activity. So as we move forward, we will be studying what exactly activity means and how it is quantified and what is the relationship. All right. Now, as far as uh, I hope you are all undergraduate, right?
Yes, sir.
So you might not have come across further this one. So as far as this stage is concerned, you understand that activity is the ability is a property of the material or a particle to uh, for external interactions. So that till that you can try to understand further as far as geotechnical engineering is concerned, how it is defined, the exact definition and how it is computed, we will be seeing in most probably in next week. So hence increase in specific surface area is due to reduction in particle size and it results in increase in activity. So option 4 is right. So moving to option 3, question 3, which of the following instruments can be used for elemental analysis of soils? Which of the following instruments can be used for elemental analysis of soils? Option A, X-ray diffractometer. Option B, scanning electron microscope. Option C, X-ray fluorescence spectrometer. Option D, all of the above. Which of the following instruments can be used for elemental analysis of soils? Option A, X-ray diffractometer. Option B, scanning electron microscope. Option C, X-ray fluorescence spectrometer. Option D, all of the above. Any guesses? Or do you know the answer, or do you have some idea about it?
No, sir.
The other person, Mr. Dheeraj,
Option D. Option D.
option D. So, so here elemental analysis is now, first of all, I will give a brief view why to understand why this is required. So you have seen, you might have come across several clay minerals and different types of arrangements and what type of minerals it constitutes, what type of element that it's constitute. So entire behavior of these minerals of these soils are primarily related with the mineralogy and elements that are present. So in order to quantify that, we use X-ray diffractometer, XRD, which gives us mineralogy. You can directly quantify it as you can actually get how much quartz is present, how much kaolinite is present, how much montmorillonite is present. You can get this as it is as a mineral composition, right? And This is scanning electron microscope. So as such, scanning electron microscope gives you the morphology. So what about its roughness and everything? And now when you combine this, it is shortly termed as SEM. Now when you combine it with EDS, electron dispersive spectroscopy, then you will get the elemental composition. So what does EDS mean? Any idea? What is the working principle? Any brief working principle will be fine. Any idea you have? Have you heard of SEM EDS or you are hearing for the first time? Please respond.
No, sir.
So
You
you are
heard for the
hearing for
first
the first time.
Yes.
EDS heard for the first time. SEM we have earlier.
Okay. So EDS, what happens is that uh, the person who has joined recently, you can start listening from this question onwards. So EDS is essentially electron dispersive spectroscopy. So what happens is that when SEM is scanning electron microscope. So what you do is you bombard the material with focused electron beam, right? Are you able to understand? Am I clear? So now if you place a material and you direct a focused electron beam. So now what happens is that two aspects occur. So since it is a electromagnetic radiation, it completely maps the material. So you will get the surface properties. And now and another one thing what happens is that when electron beam strikes here, X-rays will be dispersed. And based on the characteristics of the X-rays, you will capture the X-rays, and when you determine the characteristics of the X-rays, so that is electron EDS. So when you combine uh, this SEM and EDS, you will get both morphology as well as composition. So as of now, this is I hope I'm clear. Any confusions? Please let me know if you don't understand, if you cannot understand anything. Please respond, or otherwise I cannot know whether uh, you are able to understand, is my voice audible, or if you are facing any issues, uh, I cannot understand it.
Once more, sir.
Once more. Okay. So now,
Once explain, sir.
yeah, yeah. So now imagine you are keeping up a particle or a sample. Okay. So you are keeping it for analysis. So how it works is you will direct a focused electron beam. So you will uh, try to uh, try to bombard the particle with electron beams. So that is scanning electron microscope. So during this, you will get all the surface property, morphology in the sense how whether it is rough, smooth, and what is whether it is rounded, angular, or and everything. So as a you will be it is a microscope, so you will get the actual images. So this is the primary function of SEM, right? Now, when you combine it with EDS, that is electron dispersive spectroscopy, what happens is that during this process of when you hit the material with the electron beam, X-rays will be dispersed. So when you capture these X-rays and when you based on the characteristics of this dispersed X-rays, you can get a qualitative and to an extent quantitative composition of of the uh, material. What does it comprise of? Understood? Or you have any doubt?
Yes. Yes, sir.
So, in order to understand more, you can go through uh, some of the NPTEL lectures in the course called Environmental Geomechanics. That is one thing. And second, there is a course called Material Characterization, Advanced Material Characterization. So, those lectures you can see for in detail explanation of SEM and EDS. But as far as this course is concerned, the discussion is limited to this. So, and we use the tool exactly. And for further development of further enhancement of knowledge, you can go through these courses. And there are several YouTube videos that are available which explains the working principle and how it is actually quantified. Okay, and X
Okay.
now X-ray fluorescence spectrometer is gives you actual elemental composition in terms of oxides. So if your material contains any oxides and everything or anything, so it will give as oxides, chlorides, like that. So X-ray diffractometer will give you as a mineral. So mineral in the sense quartz is SiO2. It will say how much SiO2 is present. And but whereas X-ray fluorescence spectrometer will not give as SiO2. It will give oxides of silica oxides are present this much. So ferrous oxides are present to this much. These many ferrous oxides are present. Like that, uh, it will quantify like that. Understood? So based on that, we have to decode whether it is what type of mineral is it. So it will give a raw quantification of the elements that are present. But as far as this quantification is considered, all three are useful. So the right option will be all of the above. Understood?
Okay, sir.
So now moving to the next question. So XRD works on the principle of option A Beer-Lambert's law, option B de Broglie's principle, option C Bragg's law, option D none of the above.
Option C, Bragg's law.
So option C Bragg's law. What does Bragg's law specify? What is the how do you define Bragg's law in a simple equation? Any idea? If you know, you can say. If you don't know, you can say that you are not aware of.
No idea.
Okay. So Bragg's law essentially is its equation first n lambda is equal to 2d sine theta. Right. So now we have to understand what are all the terms. Now what happens is that Bragg's law, if you consider two surfaces which are separated by distance d, and when you are passing a electromagnetic radiation, a particular wavelength lambda incident at an angle theta, right? So the diffraction properties of this, uh, you might have come across this principle called diffraction, angle of incidence, this in some wave optics. So in this condition, so the uh, wavelength so n is defined as the order of diffraction, order, and lambda is the wavelength, and d is the interplanar distance. So this is d, and sine theta is the angle of incidence. So now this law relates the wavelength uh, of the electromagnetic waves that are used, and how much angle it is getting incident at, to get the interplanar distance. So how can we use it for our purpose is that every mineral has particular interplanar distance. So each mineral is separated by a particular distance which can be captured by using this phenomena. Understood? This is diffraction. So this is how actually we are based on the interplanar distance. You have a database, and there is a software known as Expert High Score. So it contains all the databases of several minerals and corresponding interplanar distances. So based based on your results, you match it with the database and you get the amount of minerals that are present. So for each wavelength, you will get certain peaks in the graph. So that is, but the basic working principle is Bragg's law. So which gives n lambda is equal, which is n lambda equal to 2d sine theta. So based on the basic working principle is the minerals are quantified based on the interplanar distance that are obtained by uh, passing X-ray through them. All right. Any doubts? Any doubts?
No, sir.
So coming to others law, so de Broglie's principle is dual nature of light, so that is not at all related. So Lambert's law is utilized in spectrophotometry. You might have come across this in your environmental spectrophotometry, environmental engineering courses. So when you keep a solution and you pass light through it, based on the concentration of any particular material in the solution, the absorbance will be varying. So which is defined as
Turbidity
yeah, turbidity, especially turbidity,
detection.
yeah, turbidity detection, sulfate detection. Uh, so those are done by a spectrophotometer, which is essentially based on the principle of Beer-Lambert's law. So absorbance is epsilon B into concentration of the solution. So B is the length of the light traveled. Absorb Epsilon is the molar absorptivity, and A is absorbance, and C is concentration. So based on the concentration, the absorbance value you will get, and with that you will quantify what is the concentration of the solution. Uh, So this you will be studying in your environmental engineering courses as well as in your laboratory studies. So this is just for your information. So uh, and also you can, when you extract the fluid from the soil, so that is known as pore fluid from the soil, that also you can subject it to these type of analysis to get several parameters. So that is how it is being employed in geotechnical engineering also. Any doubts?
No, sir.
Now coming to the next question. So which of the following deformation mechanisms are negligible in case of soils with rigid boundaries? Bending, rolling, crushing, none of the above. Which of the following deformation mechanisms are negligible in case of soils with rigid boundaries? Option A, bending. Option B, rolling. Option C, crushing. Option D, none of the above. Any idea?
I think option B, rolling.
Why do you think so?
Because rolling generally in lateral directions.
Okay. Actually, you are right. So when you consider rigid boundaries, uh, it is you don't allow deformation in the lateral directions also. So when you fill the particles like this and you apply load, so the only aspect this is they cannot roll over this side. So only aspect in this is when the particles are more platy structures, they will bend, which occurs in clays. And one more thing is, since they are not able to move laterally to accommodate the volume change, so what they will do, what other mechanism that may prevail is crushing. So the grains might crush based on the crushing strength of the grains. So that will not occur. That will not occur in an easy manner. So you will require very high stresses for the grains to get crushed completely. So bending can be a phenomena. Crushing can occur, but rolling is restricted completely. So the deformation which is negligible is rolling. Hope I'm clear, right? Any doubts or any other thing that comes to your mind you want to get clarified? You can ask. Shall I move to the next question?
Sir, how bending will occur, sir?
Okay. So you know that bending. Uh, so when you have
There
a,
are number of
yeah,
particles, na, sir. Very
yes,
small particles are there.
yes.
How will be bending will occur, sir? If the structures are large, like suppose a beam or lintel, anything, they will bend, sir. But small particles, clay, example, clay seals,
Hmm.
very small, how they can bend, sir?
See, that is why when bending will occur. So when you have a relatively large slenderness ratio, right? So when your length is
Yes, sir.
more predominant than your
Then
width.
thickness, it's
So
thickness.
in that case, uh, as you rightly mentioned, beams get deflected, that is, they undergo bending. So similar way to this scale, if you consider this scale, if you zoom it, and the load is acting in any direction on this flaky particles or plate particles, especially in plate particles, they tend to deform a bit. So I'm not saying that you can quantify this, but the reason for this deformation, so why, so you have to understand why this occurs. So when you apply load, what tends to happen? There is a tendency for volume change to occur of the entire sample, right?
Then it is negligible, no, sir. We are not quantifying that. That's why
So
negligible, no, sir.
yeah, so let me come to that point. So when you apply a load, the ideal thing you expect is that it undergoes volumetric deformation, right?
Yes,
So when you now if you now the next question which comes is what causes, so the boundaries are rigid. So what causes this deformation? Where, how much deformation, uh, what can predominantly cause this deformation? So two things which come to your mind is, as a logical conclusion is, you can either the particle can break, right? So which gives more compact packing. Understood? Are you able to get it? So
yes,
when a
sir.
when a grain gets crushed, so it will get crushed into finer particles. So it will accommodate in the available pore spaces. So the it contributes to some volumetric deformation. Similar way,
Yes, sir. I got it.
one more possibility is bending. So I'm not saying that as far as this conditions are concerned, the deformation might be very less. So here the aspect which you should understand is what are all the probable mechanism that that a soil sample can undergo during this deformation. All right. So that is the major takeaway that is being uh, uh, displayed to you. All right, or demonstrated to you. Understood?
Yes.
So now moving to the next question. Which of the following mechanisms are predominant in granular soil? I think this question has been discussed last week also, or last or before, the week before. So it is, as you know, it is friction.
Friction.
All right, and as you study uh, soil water interaction, you will understand what aspect of cohesion comes in granular soils. So there, in some cases, you get pseudo cohesion. So that time we will discuss uh, what gives rise to it. All right. So coming to the next question, clay particles are surrounded by dash layer. A
Adsorbed what?
absorbed
Absorb
water, B free water, C double layer, option D none of them. You are saying something.
they are surrounded by
Adsorbed what,
to
sir?
absorb water also in double layer also, but more close is absorb water.
So first you have to first to understand this completely. So first we have to understand uh, how the vicinity of the clay particles looks like. So you know that clay particle is plate-like structure, so which is essentially of negative charge, right? So this negative charge and the end will be positive charges mostly. So this negative charge attracts the positive ions from the pore solution. So the first layer will be known as sorbed layer or adsorbed layer, or another name, more technical name is Stern layer. Stern. Stern layer, because it is named after the scientist Stern, who first detected this in colloids. Stern layer. So here the ions are closely adsorbed on the surface of the clay mineral due to the positive charges. And further you move, when you move away, this particular layer is known as diffuse layer. Diffused layer. Okay. This is also known as GOI. GOI. GUOY. Sorry. GOUY. Gauss diffuse layer. This is also named after the scientist. So when you compare these two, and here further away is free water. So this is how uh, schematically clay mineral, surrounding of the clay mineral looks like. So when you combine these two, it is known as diffuse double layer. So when you dissect these two, you will get stern layer. First is stern layer or adsorbed water. Second is diffused layer, and third is free water. So as you rightly mentioned, the option is adsorbed water. And one more interesting thing is, recently people have found out that these type of diffuse double layer exists in granular materials also. There are now uh, research papers which have uh, established the presence of diffuse double layer in uh, granular materials, that is quartz and granular materials, in the sense quartz feldspar, etc. So especially in silica they have especially in quartz they have established the presence of this double layer. So, and one more point is, now the this is also positive charges. So how these two, what type of interactions uh, prevail between these two layers? Any idea? First of all, are you able to understand this, or you are finding it too much?
Yes, sir. Understanding.
So now, what type of interactions occurs between these two, stern layer and this diffuse layer? Any idea? What law does it follow? So these two layers interact by obeying Coulomb's law. So most of the interactions are Coulombic interactions. Coulombic interactions. So they obey Coulomb's law, right? So most of the basics for this clay mineralogy and these aspects are taken from colloidal chemistry. So which you would have studied in 10 plus 2, surface chemistry, right? So most of the aspects uh, uh, were adopted from this. And there is a very good book called Clay Mineralogy by Grimes. So you can also refer to it for a deeper understanding. All right. Any doubts? Any clarification?
No, sir.
Now coming to the next question. So vitrification. Vitrification involves applying which energy to soils? Vitrification involves applying which energy to soils?
Thermal energy.
So where you have come across the term vitrification? Have you come across anywhere? You can see in
Uh,
day-to-day life.
Mainly tiles, sir. Vitrified tiles are there, no, sir?
Yeah. So vitrified tiles is nothing but they will burn the clay at very high temperatures. It is similar to
Yes, sir.
bricks are also similar are also prepared by similar process. That is vitrification. So vitrification essentially means by imparting very high temperatures and thermal energy, you make uh, what to say? You make if you consider it in clays, you heat the clays at very high temperature to make it a very brittle material, right? So that is that is what vitrification is. So now, as you said, vitrification involves applying thermal energy to soils. So tiles are also a kind of clay. So in that case, most of the tiles are clays. So these clays are getting vitrified. So in order to make them brittle. So by imparting thermal energy. Understood? Clear, right? Any doubts?
No, sir.
Coming to the next question. Which of the following statements is not correct? Which of the following statement is not correct? Water can take only compressive stresses and no shear stresses. Pore water dissipates faster in fine-grained soils. Organic matter imparts compressibility to the soil. Moisture absorption capacity of clays follows the trend. Smectite greater than illite greater than kaolinite. Which of the options are not correct? Any answers or any idea? Any logics?
I think option B. More water dissipates
B, sir.
faster.
Pore water dissipates faster in fine grains.
Okay. So why can't it be option A?
Fine grained soils have very less pores, no, sir.
No, no. Why can't it be option A?
Sir, water cannot take shear stress, sir. By
Mm-hmm.
Newton's law of viscosity,
Mm,
shear stress should be zero for water.
good. So water cannot take shear. That is why you are not able to stand on water,
Water.
right? So so this option is ruled out. So when you study further in shear stresses of soil, you will come across this more. And organic matter imparts compressibility to the soil. So that is relatively well known because it is prone to degradation. So the organic matter, this is right. So this is not the answer. So as you rightly mentioned, pore water dissipates faster in fine grained soil. So the uh, the ease with which water flows in fine grained soils will be lesser, since since their pore sizes are less, their way, that is, since their particle size itself is less, the water has to travel a longer path, so it takes more time. Understood? Any
Sir,
doubts?
fourth option explains it.
Okay. So
Fourth
you are
option.
clear with the other three options, right?
Yes, sir. Fourth option is something confusion.
Okay. So here the moisture absorption capacity of place. So moisture absorption capacity is indirectly activity. Is indirectly specifying the activity. So now if you want to quantify activity, you have to relate it with which parameter?
Minerals.
Minerals is one thing, basic parameters. Which parameter governs the activity?
Waters.
No, property of
Uh,
the mineral or
uh,
grains. Which property of the grains governs it? It is specific surface area, right?
okay.
Understood? We have seen in initial questions, right? So specific surface area is the governing parameter. So here smectite is similar to Montmorillonite. So it has a specific surface area of about 800 meter square per gram, and illite has around 100 to 120, I guess, roughly. And kaolinite has 50, the range of 50 meter square per gram. So hence moisture absorption will be more in smectite, illite and kaolinite. So this option is also right. So this is also is not our answer. So as it is
ये
obvious,
छोड़ दीजिए छोड़
pore water
छोड़
dissipates
छोड़ने
faster
दीजिए।
in fine grained soil. All right.
अभी मैं हूँ इसके ऊपर थोड़ी देर बैठूंगा।
Please switch off the mic. Uh, Now moving to the next question. Which of the following is not a mechanism of deformation of soils? Which of the following is not a mechanism of deformation of soils? Option A, particle crushing. Option B, particle bending. Option C, particle rolling. And option D, particle slipping.
ऑप्शन डी पार्टिकल स्लिपिंग।
C, sir. Rolling. Earlier C, another.
Now
Earlier
here,
question.
no, there I have specified the particular boundary condition. Here it is universal. So
Yes, 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 sir. Yes, sir. Okay, okay.
all three are the deformation mechanism. Slipping is not the mechanism. So this is the answer. Understood? Now moving to the next question. Which of the following statements is correct? Bacteria preferably attached to the face of clay particle. Isomorphous substitution is the capacity to attract cations from water. In clays, cation replacement ability is greater for smaller valence ions. Cation concentration increases with an increase in distance from clay particle in water. You have to pick the correct statement. Bacteria preferably attached to the face of the clay particle. Isomorphous substitution is the capacity to attract cations from water. In clays, Cation replacement ability is greater for smaller valence ions. Cation concentration increases with an increase in distance from clay particle in water. Which option do you think?
I think option B, isomorphous substitution with the capacity to attract cation from water.
Okay. So why A is not the right answer? So now we will analyze
Because
option.
bacteria is not attached to the phase, it's attached to the site mostly.
Why?
Uh, on the side there is a positive charge,
Okay.
uh, and at the this phase negative charge.
Okay. Then
Side
why
by side.
bacteria should attach to the positive charge?
That I can't say.
Okay. So as far as option A is considered concerned, bacteria are predominantly negatively charged. Their net, even though they are living organisms, they are known to exist in a relatively negative charge. So that's why they get attracted towards the edges which are positively charged. So that is the reason. So the first option is not right. So coming to the second option, isomorphous substitution. What do you mean by isomorphous substitution? How do you define it? What conditions do they occur? I'm sure you have come across this if you have watched the lecture, but what did you understand from isomorphous substitution? Anyone? Any idea? If you know, you can say. Whatever you know, you can say. If it is right, then fine. If it is not, then I'm here to correct it. Or if you don't know, please say that you are not aware of it.
Can't explain.
Okay. So, but you have heard the term, right? If in lectures, you have been I'm sure you have been introduced to this term. So isomorphous substitution is morphous. What does morphous mean? Morphous indirectly means size. So what happens is that isomorphous substitution is an exchange, or not an exchange, it is a replacement of lesser positive ion which are having similar ionic size. All right. So now in a mineral you consider silica. What is the valency of silica? What is the charge of silica? If maximum charge that can be present. Si, is it, yes, silica exists in positive or negative? Please respond.
Negative.
Silicon ion. Silicon exists in +4. It is similar to carbon since it falls in the same group. And if you take aluminium, aluminium is +3. So in many cases in clay minerals, silicon +4 is replaced by aluminium +3. So now aluminium ion which is of lesser positive charge is replacing cation with higher positive charge. But the major condition is that both of the sizes should be comparable. Almost there should not be much difference between the ionic sizes of these two cations, right? So in that case, when this type of substitution occurs, when this type of replacement occurs, with this is known as isomorphous substitution. Two conditions are there. You can note down shortly, uh, which is the replacing cation should be lesser positive charge, replaced by lesser positive charged ion, lesser charged cation. And second condition is equal or comparable ionic size. So when a substitution occurs under these two conditions, we term this as isomorphous substitution. All right. Any doubts? Any doubts?
No, sir.
Now, in the case of lesser cations means it can be magnesium also. Magnesium plus 2, calcium plus 2, these things also. So these ions are usually found in the pore water that is present. So its ability to attract is isomorphic substitution. This is right. So third option is in place cation replacement ability is greater for smaller valence ions. So that is not true, because more the substitution, more lesser the valency, lesser will be the replacement ability. So hence this is not right. So the cation replacement ability will be directly proportional to the valency. More the valency, more will be the cation replacement ability. And fourth one is cation concentration increases with an increase in distance from clay particle in water. So what happens to the cation concentration? It increases or it decreases?
Decreases.
So the ideal curve will be, if you take a distance here d, that is distance from the clay surface, and if you take cation concentration c, cc, maybe it will be like this, right? So it will be almost an exponential curve. So this is also not the right option. So the only right option is isomorphous substitution. The statement regarding the isomorphous substitution, right? Any doubts or any other things you need to get clarified, or you need to know?
No, sir.
Then we can proceed to the next question, question 12. So the activity of the particles depends on
Specific surface area.
specific surface area. So now the question might come as I think some of them were not present in the first when I was discussing the first question. So it is specific surface area is defined as surface area by mass. So mass is in turn dependent on density, volume, and etc., area and everything. And subsequently specific surface area is dependent on total surface area by mass. So now even though here you have other total mass, density, and volume. The single parameter which engulfs all the other parameters such the primary, the quantifying parameter is specific surface area. So that is why the answer is directly specific surface area and not other three. So you can directly relate it. So that is why the answer is option D. Clear? Can we move to the next question?
Yes, sir.
If you have any doubts, you can ask any time in between. So the type of forces occurring within the soil grains. Option A, body forces. Option B, surface forces. Option C, none of the above. What type of forces exist among the soil grains?
Surface forces.
Okay,
Body forces actually.
okay. So is it body forces or is it surface forces? Or both? Or none? None is ruled out. You both said that said some options. So which option do you choose finally? So as both of you mentioned, both the forces occur, right? So the question here is which forces occur predominantly in which type of soils, right? So soils are broadly divided into two based on the size. What are they?
Coarse grained, fine grained soils.
Coarse grained and fine grained soil. So coarse grained is sand,
More than
gravels.
75 microns,
Yes,
coarse grained.
coarse grained,
Less than 75 microns, fine grained soils.
fine grained. So when you are having grains of larger size, that is essentially in coarse grain category, the forces which occur is purely body forces. It can be friction, it can be uh, gravity. So it is purely so. And one more thing is most of the coarse grain soil are inert, right? They are stable, right or wrong? If you take sands,
Yes,
gravels,
sir.
they are not they don't have any surface charges, right? So their behavior is purely governed by that is predominantly to a almost it is governed by body forces, coarse grain soils. Whereas if you come to fine grain soils, particle size is very less, right? So the weight of the particle is does not play a significant role. Whereas if you take two grains and all the grains, both the grains are that means if you take a sample, all the grains are charged, right? So in this case, what type of force occurs between these two grains? What type of either it will attract or it will repel? So it is mostly electrostatic forces. So electrostatic forces and other electromagnetic forces are essentially surface forces. So if you consider fine grained soil, surface forces will be predominant, and if you take coarse grained soil, body forces will be predominant. And if you generalize it as soil grains, both the forces are these forces are the one which governs the entire soil behavior. All right. Any doubts?
No, sir.
Now we can move to the next question. Arrange the ions aluminum, lithium, and ammonium ion. Sorry. Ammonium in the increasing order of cation exchange capacity. Arrange the ions aluminum, lithium, and ammonium in the increasing order of cation exchange capacity. How will you arrange it? Which property do you see for comparing the cation exchange capacity? First primary property is say don't bother about right
Number
answer.
of free electrons are charge.
That is what is it known as free electrons?
Positive charge, sir, which are ready to lose.
It is valency, right?
Yes, sir.
So what is the valency of aluminum?
3, right?
Plus 3, right?
Plus 3, yes.
Lithium is
Lithium also 3, sir.
3
1, sir. 1.
plus 1. And ammonium is
4.
NH4. NH4. This is also single charge.
Mm,
Now you know the valency of these ions. So what is the basic uh, how you compare cation exchange capacity between these ions?
More valency electrons, more will be cation exchange.
So which will have the highest cation exchange capacity?
Aluminiums.
Aluminum. So option A and option D is ruled out. Right. Now
Yes.
how will you compare lithium and ammonia? Which will have more cation exchange capacity?
Lithium, sir, because it is not bonded with any.
No.
I think ammonia already nitrogen hydrogen are bonded, no,
Hydrogen is
sir.
there, but valency is one, right?
That is also correct, but lithium is single.
Here the next condition which you have to consider is ionic size. So ammonium has higher ionic size. So ammonium cation exchange capacity will be more and followed by lithium, right? So uh, lithium, ammonium, and aluminum. So this is the order. So when you have equal valence, you have to compare the ionic size, right? Understood?
Yes, sir.
Now coming to the next question. The net charge in a clay particle is, what is the net charge in clay particle?
Positive.
Net charge, net charge.
Negative.
Net charge is negative always because its edges is positive. Its face have negative charges. So the net charge will always be negative in clay. So the option is here. Now coming to the grain structure. Which of the following grain structures prevail in clays? Which of the following grain structures prevails in clays? Option A single grained, option B flocculated, option B dispersed.
Flocculated.
Did you should read the question carefully. It is a multi-answer question.
Sir, dispersed clay is remolded clay, na sir.
Anything
Flocculated,
it can exist, na?
sir. Single grain may be definitely sand and other, sir.
Mm-hmm.
Honeycombed.
What about honeycomb?
Honeycomb even graded, sir, and uniform grade of size.
If you take uh, sands, single grained, though they also can be uniformly sized, na? Why they need to be in honeycomb? Okay, as far as clays are concerned, what do you think? You said flocculated, it is right. You said
Dispersed
dispersed,
also.
it is right. What about honeycomb? What is your verdict?
Maybe silts, and they are not cohesion, sir.
Mm-hmm.
Silt, I think, sir. Honeycomb.
Yes. So single grained is mostly coarse grained soils, sands, gravels, and flocculated and dispersed is for clay. Honeycomb is for silts, since their particle size is less and they are not charged, right? So the option will be B and D. Understood? Any doubts?
No doubts.
Are you able to understand, or you are just saying you are having no doubts?
Understanding, sir.
If you are not understanding, or if you are finding anywhere any difficulties anywhere, you can say to me. Okay.
Okay, sir. Definitely.
Now coming to the next question. What type of grain arrangements prevail in flocculated clays? What type of grain arrangements prevails in flocculated clays? Option A edge to edge, option B edge to face, option C face to face, option D all of the above.
Option C, I think face to face.
Okay. So how does a flocculated structure looks like? Now, if you see flocculated structures, so this is a typical clay mineral, right? It is a flatty structure, right? Now, flocculated will be the structure will be when flocculated structure will form. That you have to understand. Okay. So the flocculated structure will form when the net. So as I already mentioned, there exist what type of forces between two clay minerals, clay particles, not minerals, clay particles,
Electromagnetic force.
electromagnetic and electrostatic forces. So
Yes.
if the net force of the system is attraction, so electrostatic force is either attraction or repulsion, right? Right or wrong?
Right, sir.
So when the net force on the system is attraction, net electrostatic force is attraction. So then the structure which will result is flocculated structure. So flocculated structure will be essentially like this, like this, right? Because the plate, the this the face contains negative charge and the edge contains positive charge, right? So due to the net attractive forces, so it will prevail in this condition. So flocculated clays will have both edge to edge structures and edge to face structure, and face to face occurs in dispersed condition. Now you mentioned somewhere uh, it is remolded, right? You mentioned that dispersed structure occurs when you remold it, right? What is meant by remolding? What do you do to remold it? How will you remold the sample?
Disturbances of already existed mm, shapes, sir.
Yes. So
Maybe.
now you consider you are disturbing it by applying an external load. Okay.
Yes.
Now what will happen to this structure? How it will be? How it will get rearranged?
Arranged with any specific pattern.
Orientation, right? So mostly
Oriented. Yes.
if you are applying load like this, mostly it will get arranged in this similar like this, right? Not exactly parallel or something like this, right?
Yes, sir.
So this is dispersed structure. So this is dispersed structure. So what type of arrangement this is? So here the net electrostatic interaction is repulsion, right? So here you will have face to face arrangement. This is dispersed. face to face. Understood? Any doubt? Any doubts?
No, sir.
Understood, right? Now moving to the next question. So match list 1 with list 2. So the left column specifies the type of soil and corresponding structures which they predominantly existing. So match the following. Sands exist as
Single grain structure.
it exists as single grained. Sills exist as
Honeycomb.
honeycomb, and clays exist as
Flocculated.
calculated. So it is fairly straightforward. Now moving to the next question. So match list 1 is list A. Same, relatively same. Clay minerals will get in flocculated structure. Organic matter is peat.
Peat.
Intergranular cement is
Honeycomb, sir.
honeycomb.
Rock minerals are single grain structure
Primary
sand.
rock minerals are single grain. What are primary rock minerals?
Silica, feldspar,
Quartz,
quartz, yes.
feldspar, etc.
Hornblende, etc.
Uh, it can be calcite, it can be dolomite, etc. Any any mineral that make up the that is uh, source kind of source before weathering. Now coming to the next question. Match the following clay minerals with the type of bonds present in them. So elite, smectite, montmorillonite, kaolinite.
A light potassium bond.
Okay. Others?
Montmorillonite, van der Waals, and smectite also.
Okay.
And this rest is kaolinite with hydrogen bond.
Okay. Now to give some insights, you know that different type of clay arrangements, right? What type of clay arrangement? 1:1 and 1:2. Have you come across this? Have you come across this or not?
Not
So clay minerals. So now the one aspect is you just understand what type of bonds that are present. Second is you visualize them. So what happens is that there are two types of clay minerals. One is 1:1. So 1:1 is essentially clay minerals are aluminosilicates. Okay, essentially clay minerals are aluminosilicates. Understood? What does this mean? Aluminosilicate means what does it contains consist of predominantly? Hmm? Any idea? It is there in the name itself. Aluminosilicates means what elements that it contains? So it contains aluminum and silica, right? So now then you know that clay minerals are interplay of arrangements of aluminum and silicon. So there are two types of arrangements, which is 1:1 and 1:2. 1:1 in the sense each a single clay mineral comprises of one silica. Sorry. So this is fairly technical, so you have to note it down. So silica is represented as trapezium. This is how silica is represented in soil mechanics. Silica sheet, SiO2 sheet. So this represents what? Silica. O, O, O. Is a tetrahedron. These two oxygen, all the oxygen are shared with the further silica. So this is represented as trapezium, and alumina is represented as rectangle. So this is a tetrahedral sheet and this is a octahedral sheet. It is essentially AlOH, aluminum and hydroxide. So if a single clay mineral consists of this arrangement, one aluminum and one silicon, it is known as 1:1 arrangement. All right. So kaolinite is one example of this arrangement. Aluminum 1:1 arrangement, and both these, if you take two minerals, aluminum, silica, this is one mineral constituent, and another is aluminum, sorry, silica. So these two are bonded by hydrogen bonds. In case of kaolinite. Okay, any doubts? If you are unable to understand, or if you have any doubts, please ask.
Sir, how to identify that this mineral is illite or montmorillonite from the structures?
From that's what, see now, this is for kaolinite. Okay, kaolinite is a 1:1 1:1 arrangement with hydrogen bonds, and if you take illite is 1:2. That is, one aluminum is sandwiched between two silica sheets. All right. So this is 1:2 arrangement, and when you take uh, two sheets like this, similarly, now these two are bonded by potassium bonds. In case of illite, and similarly in case of montmorillonite and smectite, this bond is van der Waals force of attraction, very weak bond, van der Waals bond. Okay, so based on the nature of forces, and in between smectite and montmorillonite, the aluminum, the content of aluminum, partially aluminum will be replaced by magnesium. So this entire thing will be captured based on the, now you can understand why XRD is being used. Now if you see, based on the type of bonds, the interplanar distance will vary. Understood? Right or wrong? Those who have been present from the earlier discussions, so as I mentioned, Bragg's law, X-ray diffraction, which is used for identification of, which is used for quantification of minerals. So based on the nature of bonds, its interplanar distance, that is distance between two minerals, will vary. So based on this variation, you will get the amount of you will get the corresponding diffraction response from XRD. So that is how you will be quantifying how much this mineral is present to a what extent. Understood? Any doubts?
Yes, sir.
Any confusions which you want to get clarified? Shall we move to the next question?
Yes, sir. Yes, sir.
Our next question is a small problem. So you have come across the term cation exchange capacity. So now how to calculate it? Okay. Now the question is now first you have to understand the cation exchange capacity means, you know that it is the it is the ability of the uh, s- mm, ions to get exchanged, that is to get absorbed to get absorbed. So how it is defined is that it is defined in the unit of milli equivalents per 100 grams. Okay, so I will solve this problem. So now what we will do is, 100 gram of dry soil sample absorbs 300 milligram of magnesium, 300 milligram of calcium, 300 milligram of calcium, right? Now cation exchange capacity in milli equivalent per 100 grams. Now what you have to do is, first of all, you know the amount of calcium that has been absorbed amount. How much is the absorbed amount? This 300 milligrams, right? Now what is the, how will you represent calcium ion? Calcium, what is the valency? Please respond.
I think Ca2 positive.
This is calcium plus 2. Are you able to follow till this one, or you are finding it confusing?
No, okay, please proceed.
So calcium is represented as Ca plus 2. Now the next step is, you have to calculate the equivalent weight. How will you calculate the equivalent weight? How equivalent weight is defined? So you have to go to your plus 2 chemistry. So The equivalent weight is defined by molecular weight by valency. Now, what is the molecular weight of calcium? Sorry, not molecular weight, atomic weight. Or molecular weight. There can be molecule also. Molecular weight. So, molecular weight of calcium is 40 grams, and valency is +2. So, the equivalent weight is 20 grams. Now, the cation exchange capacity is CEC is defined by adsorbed weight by equivalent weight. So you need this in milli equivalents. So you can keep this as 300 milligrams itself by 20 grams. So what you will get? 15 milli equivalents for how many grams of dry soil? 100 grams of soil. So this is how cation exchange capacity is calculated. Any doubts? Did you understand, or please let me know if you are able to follow, or
Sir, is
yes.
100 grams of soil.
Mm-hmm.
So if you see the formula is equivalent weight and CEC. So there is no relation of that 100 gram of soil. So how can we say that it
No,
will
no, no.
be only
Actually,
for 100 grams?
this is actually CEC is defined by this quantity per 100 gram of the material. Okay, so that this aspect you will get equivalent. That is what total weight, that is absorbed weight by equivalent weight. You will get how many equivalents of ions is getting absorbed. That is per 100 gram how much it is getting absorbed. That is what CEC is standardly defined.
Okay, sir. Okay, got it.
Okay.
Yes, sir.
Any other confusions?
Sir, can we get the questions and solutions in our login, sir?
Questions and solutions, as such, you will not get it separately. The PPT will be uploaded along with this whatever we have discussed, and the link to the video will also be uploaded in your login.
Okay, sir.
So you can go through that.
Okay, I was stuck in somewhere, so that I can't join early.
Fine, fine. That is not an issue. So this
Mm.
session, with this session comes into a conclusion. So as far as a concluding note, this session will take place every week on Saturdays 5 to 7 p.m. So learners are encouraged to join and solve the problems along with me. So I hope this session was useful, and the recordings and PPT will be uploaded in the NPTEL login, corresponding NPTEL login. So you can go through anytime if you want, and you can ask your queries if you have in the further sessions also. So
Thank you, sir.
okay, so with this we can wind up the session. So meet you next week. Thank you. You can leave the meeting.